Hello everybody, this is going to be our video lecture on phasors and legged races, so let's just get right into it. First of all, there's a quiz, and so I'd like everyone to check out the quiz. First of all, there's this butterfly network that I have 2 copies of the exact same butterfly network to leave you work to, to write on it, to do whatever you need to do to track what the critical path length is, and to encircle it if you want to do it separately. The dependencies here, like inside of each node, you'll find the work for each node. And dependencies are sort of, this is sort of the sequential dependency. So for each iteration, there's a dependency on the previous one. And also the butterfly has these bonus dependencies which go to their neighbors. This looks a little bit like the neighbor distance situation in SCAN. So first, work on that part of the problem. The next one is about iterative averaging. This has to do with fuzzy barriers and what work is shared and what work is local. So by that I mean, if you imagine this 11 long array that's been sliced into 3 ranges, A, B, and C, which of these indices is work that your neighbors are interested in, and which one is are indices where you're the only one who's interested in. So shared work is something that your neighbors are interested in the answer or are depending on it. And local work has greater flexibility. That's the ones that you're the only one who needs to worry about that. So if everyone could dig in on that, we will move on and discuss it when you're done. Unpause when you're ready. Okay, so let's go back. First of all, like just from the S&Q, can we go over the butterfly network? So we talked a little bit, I just talked about like what this thing is. Let's talk about an approach to making this work. So the idea is that you would, you choose, what I do is you choose the worst of the 2 paths. This is critical path length, so you're looking for the bottleneck, so you're looking for the most work. In this case, it starts off, unfortunately, as both the same. So you could choose either one, and it's like, all right, so that one's 10. If I move on, this one also can choose either path, it's 6. This one is 17 because it could choose the 8 or the 5 to combine with the 9. It chooses the 8 because that's larger. This one also chooses the 8 path is because 15 is greater than 12. It just goes on, and just everyone chooses their worst candidate, and that becomes the sort of path up to this point. We move on to the next layout, and we do the exact same thing. So this one would choose, it's like, well, I can do 6 and 10. That would be 16. That sounds nice. But I really need to choose the larger of the 2, so now I'm 23 because I've selected this path. And you do that for all these levels, do that for all these levels again, right? Once again, choosing the worst path. And so now you look for the worst possible situation of them all, 31, right? So that's going to be our critical path length. And we just trace back to how we got here, okay? And so now I know that that's the critical path for this guy. Okay. Now, for this one, I have a little bit smaller one. It's just how it is, but that's your critical path length. So for this, let me see which example I had on here. Let me go back. For this example, the path is going to be 8 plus 7, which is 17, plus 6 is 23. That's going to be 31. If I look at, excuse me, this guy, I gave you a slightly smaller one. It was just the little one because I didn't want you to have to do the whole full path. So this one is going to be just these 3. So 19 is your critical path length here, and that's the critical path for this particular example. I have it worked out on a slightly larger one because I feel like it helps to see the differences. But the quiz has a little bit shorter one to make it so you don't have to do too much labor on the quiz. All right, so let's talk about this one. This one is directly related to fuzzy barriers and how it relates to the iterative averaging one. So hopefully everyone got their answers on this, which indices are the shared work. These are the ones on the boundaries, right? So for A, the only one that anybody cares about, that is its neighbor B, is going to be 3. B has both sides, 4 and 6 someone cares about, and C only has 7 that their neighbor on this side counts. And this, what I want you to imagine is more in the iterative averaging, instead of being 11 along, this would be like 1,000,000 long. So if it was 1,000,000 long and there was 10 slices and there were 100,000 each, right, there'd be still would only be the 2 on the edge that mattered. You do those first. And then the 900, the 99,998 in the middle, you could do on your own time. And what this allows you to do is, instead of doing sort of a normal, just turning it into a phased version of this loop where you flip it inside out, you can split it up, and you can split your shared work and your local work up. And so in this case, the shared work would be doing your 2 edges, and sort of going back here, do these 2 first, right? And then you can do all your local work. In this case, it's just 1, but I want you to imagine the 99,998 in the middle you could do. And so in between, you say, oh, instead of arriving in a wait advance, I've arrived. By the way, if my neighbors are interested, they can go ahead and move on. So you stop making people wait on you. Then you do your local work, which you're the only one who cares about. Then you wait on, the phaser that you're interested in, right? So this is nice in that, sort of the shared work gets done right away. And I actually don't care about these edges. Usually, like, I'll just do both of the outsides in my task first, and then be like, I've arrived, now I'm gonna do my other 99,000 in the middle, right? And that's my local work. So that's the answer to that one. There's a video on this subject and phasers in general. I highly encourage you all to watch it. I shot it separately and embedded it on the wiki so that it's there for you. And also there's a video specifically about our legged race studio that we're going to have today. And again, I separated that out, and I encourage you all to do that. And this is the studio, and hopefully you'll have fun with it. It's an example of how to do both the phased for parallel for loop, excuse me, a phased version of a sequential and a parallel for loop working together. And then it does the point-to-point synchronization, breaking down the difference between n+1 legged race versus n/2 3-legged races. So hopefully you'll have fun. Good luck with that.